Hi everybody, Physics Ninja here. Today we're going to do a very quick, simple video on how to calculate the magnetic flux through a prism. So what I have here is a prism that has various lengths, 30, 40, and 50 centimeters along the diagonal. And what I'm going to do is I'm going to place this prism in a constant magnetic field. The field is pointing along the Z direction that I've defined this way. And what I want to do now is calculate the magnetic flux using our equation. We have some simplifications to make because in this case the field is constant, and we're going to look at the flux through the various surfaces of this prism. I'll show you how to set it up, and then at the end we're going to calculate the total flux through the prism by adding up all the different contributions. All right, let's get started. If you have any questions, leave them in the comments section. Give it a thumbs up if you liked the video. Remember to subscribe to my channel. All right, so to get started, what we're first going to do here is that we're going to simplify our equations. It's usually defined like this. However, if the field is constant, which it is in this case, right, it's going to be pointing only along one direction, then we don't have to worry about integrating. We would only have to worry about this equation here if the field was different at different points in space, but it's always the same. Therefore, really what you have to do is if you're only considering one surface and the field is constant, simplification is, it could simply be written like this. It's the magnetic field and the scalar product with an area vector, and I'll show you how we define the area vector in just a second. Okay, but this is a scalar product between two vectors, and this just here gives me a number. At the end we get units of Tesla multiplied by area, which is meters squared, and this here is what we call a Weber. Okay, we kind of just define it like this, WB. All right, to write down this scalar product here between the two vectors, there's two ways of doing it. Okay, and we're going to do it for each case here. Method one, what I'm going to call method one, is I'm going to use the components. So let's assume that our magnetic field B can be written in terms of three components. Bx value, a y component, and a z component to that vector. And likewise, let's assume that our area vector can also be defined in terms of components, ax, an AY, and an AZ. So one way to write out this scalar product is just to multiply the components and then add them together. So it would look something like this, BX multiplied by AX, and to that I would add BY multiplied by the component AY, and plus BZ multiplied by this component AZ. I'm going to call this method one. All right, second method that you can use to evaluate any scalar product between two vectors is you simply take the magnitude of the first vector, which is the vector B, you multiply it by the magnitude of the second vector, and then you also multiply it by cos of theta, where theta here is the angle between both of those vectors. So for example, if I have the vector B pointing in this direction, and I've got the area vector pointing in this direction here, the angle between both of these vectors would be defined as this one. You have to start the vectors at the same point. So this would be the angle theta that I would use to calculate the flux between, or the flux through this area A. So again, both of these equations actually are the same thing. They represent the same thing. They're just two different ways to represent the scalar product between two vectors, and we'll evaluate both of them for this problem. So now let's go back to this prism and identify all the areas that we want to look at and identify the flux through each area. So let's first start by identifying our different vectors. Let's start here with our vector B. The vector B is, I define it like this. I haven't given it a magnitude yet, but for everything that follows, I'm going to assume that the vector B is only pointing along the Z direction as shown in the figure here. And for now, what we're going to do is we're going to give it a magnitude. Let's assume that it's 0.15 Tesla. That's the magnitude, and the direction here is going to be, I don't need a bracket since it's only in one direction. It's pointing along the Z direction, so I'll call that the Z hat direction. All right, let's maybe highlight this vector over here. And we're going to be using this throughout the rest of the calculation. All right, the next thing we want to do now is identify what are the area vectors. Now the area vectors kind of depends at what we're looking at, but let's start with an easy one. Let's assume we were looking for the area vector defined, say, by the letters A, B, C, and D. So if I kind of draw it out, it's kind of the area here on this back wall of the prism. Okay, so let's go ahead and write that. Imagine I was looking at the area vector defined by the letters A, B, C, and D. Okay. In this case, this area vector here would have a certain magnitude. The magnitude of the vector is simply given by the area. And the area is simply going to be 40 centimeters. Right, that's this distance right here. We can call that 0.4 meters. And multiplied by the height. The height is the distance from point A to point D, and that's 30 centimeters. So 0.3 meters. Now that's the magnitude of the area. Now how would you define the direction of the area given by this rectangle over here? So to define the area, what you have to do is you simply take a vector that is perpendicular to the surface. So in this case, it would point in this direction here. This would be the direction of the area vector for the area delimited by these letters A, B, C, and D. So if you look at this vector A, it's pointing in the negative x direction. So I'm just going to write this like this, negative x. Okay, so at the end, the total area, what I have to do here is simply multiply this through. If you do that, you get 0.12. And now take the negative sign, I'm going to bring that to the front and multiplied by the unit vector. That is the area A, B, C, and D. Okay, let me just write it down here, A, B, C, and D. All right, so we've defined one area. We can try to do another one here. Let's try to do the top area. All right, the top area of the prism is this one over here. So let's go ahead and try to evaluate what is the area of this one. So it's going to be the area. In this case, it's denoted by the letters A, B, and E. So I'll just call this A, B, and E. Again, it's going to be a magnitude. So what is the magnitude of the area? Well, this is simply a right angle triangle. So it's base times height over 2. So 1/2. The base could be 30 centimeters. The height might be this guy over here, 40 centimeters. Okay, that's the magnitude. Well, what would be the direction now of this area vector? Again, if you wanted to find what the direction is of an area vector, you simply go to that little area and you plot a vector that is perpendicular to it. And notice I have a vector that's pointing away from the object. Okay, in this case, so this would be the direction of this vector here. That looks like it's the direction of the y vector. Okay, something like this. So at the end now you could just multiply everything through. It's simply going to be half of the first one, except it's going to be a positive value, right? The way you've defined it here, because this vector is pointing up. So at the end, if you multiply this through, you should get 0.06. That's the magnitude, and the direction is in the y hat. Okay, and this will be the area ABE. All right, we could do one more. Actually, you notice that the area for the bottom half, all right, the bottom half is denoted down here. That's this triangle over here. That's the triangle CDF. Is going to be the same magnitude because it's a prism here. It's going to be the same magnitude. However, the direction is going to be different. So right away, I can just write down the other area down here. It's going to be negative 0.06. And again, it's pointing in the negative y direction because, again, you go to that surface and you draw a vector perpendicular to it. Oh, that's what this one is. And this one here I would call CDF. All right, we've done quite a bit of work so far. We've got a couple more to do. Let me make a little bit more space here. Let's get rid of this, get rid of this. We haven't done the back surface, and we haven't done the diagonal surface. So let's do the back surface first. Now this one here is pretty straightforward. Let's pick a different color. So the back surface is the one kind of in the back of this prism. So the area for this one, again, the magnitude now, it's simply going to be the width multiplied by the height. That's 0.3 meters multiplied by 0.3 meters. And now, well, what do you think the direction is going to be? Again, if I think about this prism, a vector that points perpendicular to that one should point away from that surface like this. Okay? And that looks to be in the negative z hat direction. All right, so we multiply everything through. This area, the pink one that I've denoted here, kind of the back edge, would be 0.09. I'll put the negative sign in the front, and that's multiplied by z hat. And at the end, this here corresponds to BCEF. BCEF surface. Okay, we only have one more to do, and that's the diagonal face. For that one, I'm going to use a new page and show you how to do that one. All right, so the next one here is probably the most difficult one. It's the one here on the diagonal face of this prism. All right, so this here would be the area of the rectangle. It's AEFD. Let me just write it like this, AEFD. First of all, the magnitude is pretty easy to write. Right? The magnitude is basically just going to be, what is this area right here? And that's just the height times the width of the rectangle. So in this case here, it's simply 0.3. That's our height. And the length now is going to be 0.5. All right, so I know the magnitude of the vector. The hardest part now is simply to be, how do you actually evaluate the direction? Because now it's not just along one of these axes, it's actually perpendicular. I don't know how to kind of do this in 2 dimensions here, but it's perpendicular to that surface, right? It's perpendicular to that surface. So what I'm going to do now is, to make this a little bit simpler, what we're going to do is we're going to look at it from the top down. And if I look at it from the top down, basically what I'm doing is I'm looking at the x-axis and I'm looking at the z-axis. All right, and if I draw the prism there, looking at it from the top down over here, what it looks like is there's an edge over here that's 30 centimeters, and this goes all the way to point E. There's also an edge that goes along the z-axis that goes from B all the way to A. All right, and it kind of looks something like this. This is what the prism looks like. And it's not drawn properly here. This side here would be 30 centimeters. This side here would be the 40 centimeters. And this side over here would be my 50 centimeter side, right? The hypotenuse. Now the vector A is one that points perpendicular to this. And the magnitude I've calculated right here. It's this vector here that points perpendicular. Now what I'm going to do here is just draw a line that is parallel to the z-axis. And now, well, what you can do is define some angles over here. If I call this interior angle of this triangle alpha, and call this one over here, what can I call this one? I can call this one beta. All right, something like this. Now, you should be able to use some of the rules you know for triangles in order to convince yourself that if this is the angle beta, that means this one here has to be the angle beta. And the way I know that is because I know my Z rule. Z rule is if I have 2 parallel lines, that the angles here have to be the same. And you should also be able to convince yourself here that this interior angle here is also the angle alpha. And this is kind of what's important. So what I want to do at the end of the day here is I want to break this area vector A, which I know has a magnitude of 0.15. What I want to do is I want to break it down into x component and into a y component. The x component of that vector is going to look like this. This is the x component. And, sorry, the z component in this case, right, because I'm working in the xz plane, the z component is this one right here. So this is AZ. And if I know this interior angle, it's very easy to define those. So let's go ahead now and simply write it out that the vector A is going to be an x component. Now the x component is going to be the vector A multiplied by sine of alpha. And that there is pointing along the x hat direction. Okay? That's basically AX right here. Let's go ahead and just identify this. I've just used some trigonometry here. This is AX. And now to that, what I want to do is I want to add this other component, the z component of that vector. Okay, this guy here will use the cos angle. So it's going to be the magnitude of A multiplied by cos of alpha. And all of that needs to be multiplied by the z hat direction, right? That's this vector right here. And the length of that component, this is what I've defined as A sub z. All right. So we have to put this all together now. Again, cos of alpha, or if you define it in terms of beta, these are quantities that we actually know, right? If I just go ahead and use my initial triangle over here, cos of alpha, you should simply be able to write that as 30 centimeters divided by 50 centimeters, right? The adjacent over the hypotenuse. At the end, this ends up being simply 3 over 5. Okay, so you can go ahead and simplify this, and also sine theta, Then sine theta is the opposite over the hypotenuse. That's 40 over 50. That just gives me 4 over 5. All right, so that means this here can simplify even a little bit more. That means we have the magnitude of A multiplied by 4/5 x hat, and plus the magnitude of A multiplied by 3/5 multiplied by the z hat vector. All right, so that here is the vector A for this diagonal surface over here. A little bit more complicated than the previous cases, but hopefully that you understand this argument over here that I've made. Now let's put it all together and calculate the flux through every single surface. All right, so what we're going to do now is evaluate the flux through all the various surfaces. These are the first three. There's one more after the diagonal one. And we're going to do it using both methods, using the components of each one and also using the other definition for a scalar product. So method one is going to be using components. So let's look at our first surface, which is ABCD. ABCD is this rectangular surface over here. It had a magnitude of 0.12. It was in the negative x hat direction. So again, if we look at our first thing, again, the vector B here only has a z hat component. That's it. So the vector B, if you were going to write the vector B actually in component form, it would look like this. It would look like 0 for the x direction, 0 for the y direction, and 0.15 for the z hat direction. Right? So therefore, looking at the first term over here, what you end up getting is that the flux is, well, it's 0. 0 because you have 0bx. So even though you have an x component for the area, it has no component for the field. So that's 0 plus 0. There's no y component for anything. And look at the last term. Although you do have a 0.15 component for bz, the area doesn't have a z component. So that is also multiplied by 0. So at the end, the flux through that surface, maybe I should use a different, let's just write it down as 0. Okay, that's the flux through that surface. How about if I use the second method? The second method would say, what is the magnitude of the vector B? The magnitude of the vector B is 0.15. That needs to get multiplied by the magnitude of the area. The magnitude of the area is 0.12. However, now the last part says cos of the angle between the area vector and the magnetic field vector. Well, the area vector for this guy points in the x hat direction. And that means that the angle here has to be 90 degrees, and cos of 90 degrees gives me 0. Okay, so we get 0 for both of those cases, as you would expect. Both methods have to give you the same answer at the end of the day. All right, let's look at the triangular surface over here. Our area vector is our second one here. Okay, it has a magnitude of 0.06 and it's pointing along the y direction. So in this case here, my magnetic flux through that surface, 0bx multiplied by 0ax plus the magnetic field component in the y direction is 0. It's only along the z direction. And the component of the area along the y direction, yeah, there is one here, but at the end it gets multiplied by 0, so it doesn't matter. We also have a z component for the magnetic field, but we don't have a z component for the area. So at the end, the magnetic flux going through the top surface over here has to be 0. Now you can use method 2. Method 2 looks very, very similar. The magnitude of the magnetic field is this. The magnitude of the area in this case, I'm sorry, it's not 0.12, it's 0.06. However, still have cos of 90 degrees in there. So at the end, you get 0 for this magnetic flux. And again, this one here is going to be 90 degrees because its area vector is pointing perpendicular to that surface, right? And the magnetic field is pointing along the z direction. The angle between the area and the field is 90 degrees. All right, let's do the next one. The next one is a squared surface over here for this prism. That's the area BECF down in the back. The magnitude is 0.09. The direction is in the negative z hat direction. So let's use method 1 to calculate the magnetic flux. This is what it would look like. Well, it's 0 multiplied by 0. Both of those components end up being 0. plus 0 multiplied by 0. Both of those components are 0. However, you got to be a little bit careful now. The next one is the component BZ. BZ is our magnitude of the field, right? 0.15. It only has a z hat component multiplied by the magnitude of the area, which is negative 0.09. All right, now if you go ahead and you multiply both of those numbers together, what you end up getting in this case here, carrying that out, you should get a number that's 0.0135. So, and we have a negative sign, right? 0.0135. And that's in units of Tesla meter squared, which is what we call a Weber. Okay. That's our magnetic flux like this. All right, how about if I use my second definition? The second definition would be the magnitude of B, which is 0.15, multiplied by the magnitude of the area, which is 0.09. And now cos of the angle between both of those vectors. In this case, it's cos of 180 degrees. And cos of 180 degrees gives me my negative sign that I had here in the previous case. So 0.15 multiplied by 0.09. You notice you're going to get the exact same number. You're multiplying the same two numbers together. Okay? And the cos of 180 degrees comes from the fact that, well, for that area BECF, right, the vector of that area points along the z direction, or the negative z direction, the way I have it here in the figure. And the angle between both of those is 180 degrees. All right, so we finally have some magnetic flux. Let's do the diagonal surface now. So for the diagonal surface of this prism here, I rewrote what we had here for our area vector, and I just kind of substituted in the values here. So for the magnitude of that area, it's simply the value of the area, which is 0.15. So I put in the numbers here. And again, that vector is on a diagonal, so it has an x component and a y component. And what I did, I just multiplied everything through, and I wrote it in component form over here. And this allows us to right away evaluate the magnetic flux using both our definitions. Using our first definition here, what we have is the component AX, 0.12, multiplied by BX. BX is 0, plus you get 0 for the x component of the area and 0 for the x component of the magnetic field. That also gives you 0. And the last one now is you get 0.09 for the area. Z component, multiply that by 0.15. All right, and if you carry out that multiplication, you should get the same answer as what we had previously, right? Times 0.15 gives me 0.0135. Again, this is going to be in Webers. Now notice in this case here that the flux gives us a positive number, whereas through that back surface we had a negative number for the flux, although the magnitude was the same. All right, how about if we use method 2? Method 2 says you take the magnitude of the magnetic field vector, which is 0.15. You multiply that by the magnitude of the area. The magnitude of the area is simply the value of the area, which is also 0.15. Right? You get that by multiplying 30 centimeters by 50 centimeters. And now you also have to multiply by cos of the angle. Cos of the angle between both of those vectors. Remember, you have your area here, which is perpendicular to the surface. And if you look at it from the top down, it actually ends up being cos of this angle alpha. And cos of the angle alpha is 3/5. So at the end, we get 0.15 multiplied by 0.15 multiplied by 3/5. This you can simplify a little bit. I could take out a factor of 5. If I do that and then I multiply by the 3, let's get rid of this. This second term here becomes 0.09. So you could see at the end, you're going to get the exact same number for the flux, whether you use method 1 or method 2, as we would expect. All right, and the last thing you have to check is that the total magnetic flux, I have all the individual contributions here that we calculated. Many of them were 0, right, because the area and was perpendicular to the magnetic field, and that didn't give any contributions. We had a negative flux here for the back surface of the prism, which which we calculated, and also a positive value of the magnetic flux going through this diagonal surface over here. At the end, if you add up all the contributions, you should get 0. That's kind of a cool property of magnetic fields. If you have a closed surface like this prism here, it could have been any shape actually. I would have always obtained 0 total magnetic flux going through the total enclosed surface because there are no sources of magnetic fields inside. All right, thanks for watching, folks.